Alright, here we have lecture 4.1. For those of you following along in the textbook, this corresponds to section 6.1 and 6.2 from the textbook, if you want to read the material in the textbook. And it's here we introduce the exponential function. Now, the exponential function is of the form written there, where C and A are constants, X is a variable. So as usual, it's very important that you distinguish your constants from your variable. So what distinguishes an exponential function, or makes an exponential function exponential, is that the variable is in the exponent's place. That is the primary characteristic of an exponential function. The base is constant and is represented by the letter A and has a coefficient called C. Now that coefficient C is known as the initial value. Of course, it has to be non-zero, otherwise it would zero everything out, and that's quite boring. And then the base of the exponential function is known as the growth or decay factor. Now if that base is bigger than 1, you will have growth. If it's between 0 and 1, you will have decay. So let's look at these examples here. Is the function exponential? And the answer is, for number 1, is yes. That is an exponential function, and it is growing. And it has a growth factor of 2, because that's the base. Now notice it's growing. That's because the the base is bigger than 1. So as x increases, it's getting bigger. Think about 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. Every time you increase the power by 1, you're multiplying by another multiple of 2, so it is growing. Now be wary on example number 2, that is not a exponential function. That is a quadratic function. So we want to make sure we don't confuse quadratic functions with exponential functions. Their properties are very, very different. So remember, what makes an exponential function is that the variable is in the exponent's place. Now number 3, that is an exponential function. Notice the placement of the variable, and it is decaying. And it has a decay factor of 0.5. Because as x increases, you're repeatedly multiplying by 0.5, and as you know, every time you multiply by 0.5, it gets smaller. The quantity decays. And then number 4 is also an exponential function. And 9 halves. Well, 9 halves is the same thing as 4.5, which is bigger than 1. Hence, we have growth. And it's a growth factor of 9 halves. Alright, with the introduction out of the way, let's go ahead and study this from a visual perspective. Let's go ahead and look at the graph. Now what we're going to do is just plot some points. So let's just plug in x value. So say we plug in 0. Well, 2 to the 0 is 1. Say we plug in 1. 2 to the first is 2. Say we plug in 2. 2 squared is 4. Say we plug in 3. 2 to the third is 8. Say we plug in 4. 2 to the fourth is 16. Plug in 5, you get 32. So on and so forth. It's just going to multiply by 2 every time. Now let's go in the reverse direction. Say we plug in negative 1. Well, 2 raised to the negative 1 is 1 half. If we plug in negative 2, 2 raised to the negative 2 is 1 fourth. And negative 3 would be 1 eighth. So on and so forth. Let's go ahead and plot these points. So we got 0, 1, 1, 2, 2, 4. And then we've got, see here, negative 1, 1 half, negative 2, 1 fourth, so on and so forth. And we can go ahead and sketch that. Let's connect those dots. And we get this kind of quarter pipe shape. Now note the rapid growth. Notice as we move from left to right, the function is constantly accelerating. This is something that exponential functions are very famous for, their growth properties. And as we move to the left, it decays. Now notice it will never actually reach 0, because as we go from right to left, instead of multiplying by 2, you're really dividing by 2. So if I take a half, and then half of that, then half of that, then half of that, I'll never actually reach 0. Suppose you have a piece of paper, cut it in half, then cut the half in half, then cut that in half, then cut that in half, then cut that in half. Will you ever completely destroy or get rid of the paper? Well, technically no. You're always going to have half of what you had previously. So what we have here is an asymptote, specifically a horizontal asymptote. And that's because as the exponent goes to negative infinity, the exponential basically goes to 0. And if you need to review properties of exponents. So that means when we're graphing an exponential function, the horizontal asymptote is going to be given by the vertical shift. Going back to transformations from the second exam. Now the domain of any exponential function is going to be all real numbers. In other words, negative infinity to positive infinity. Note we don't have to worry about division by 0 or imaginary numbers or any complications in string. We can plug in any number we want. Now the range will depend upon the transformations and the asymptote. So the range is either going to be above or below the horizontal asymptote. And the rate of change, as we mentioned previously, for a classical exponential function, it is constantly accelerating. They're very famous for their growth properties, which is why they're used in a variety of applications, is because of their growth properties. And their decay properties as well. They're also used to model radioactive decay. But more on that later. Let's look at some graphing examples for now. So if I look at this example 1, I just took a base 2 exponential function and just added a bunch of transformations. So the first thing we want to do here is identify the horizontal asymptote. So the horizontal asymptote is given by the vertical shift, in this case 5. So it's very easy to identify the horizontal asymptote in an exponential function. And just like on the last test, I'll go ahead and mark that horizontal asymptote with a dotted line. Now let's go ahead and plug in some points. Now you might think to start at 0. Well, let's plug it in and see what happens. Well, that would be negative 2 raised to the 0 minus 3 plus 5. And if you plug that in, you're going to get basically negative 1/8 plus 5. Which is 4.875. So it's going to be very close to that horizontal asymptote, but that's not very good for graphing. A lot of times we want to have nice integer coordinates when we're graphing. So if we look at that function, we want to try and keep the exponent positive. That'll make the numbers easier to work with. So instead of plugging in 0, let's plug in, say, 3. If I plug in 3, 3 minus 3 is 0. Well, 2 to the 0 is 1. Keep in mind, anything raised to the 0 power is 1. So if necessary, go back and review your properties of exponents. So 2 to the 0 is 1. Negative 1 plus 5 is 4. And we can keep on going in this direction. If we plug in 4, we get 3. If we plug in 5, 5 minus 3 is 2. 2 squared is 4. Negative 4 plus 5 is 1. And feel free to use your calculator when computing these points. Let's go ahead and connect these. So we got 3, 4, 4, 3, 5, 1, and then I'll go ahead and mark that 0, 4.875 somewhere close to that dotted line. And let's connect those dots. And there we have it. So every exponential function will have this shape. It'll be shaped kind of like a quarter pipe or a rounded corner. Now, the directions didn't ask for domain and range, but let's go ahead and do it for fun. The domain of any exponential function is always going to be all real numbers. Right? It's a continuous graph and goes left to right forever. We can see that visually. Now, the range is always going to depend upon the asymptote. So we know the asymptote here is a horizontal asymptote of 5. And it turns out exponential functions will never actually touch their asymptote. Now, which means the graph must be completely above or completely below. Now we already graphed this so we know it's below, but a good trick is just to look at the negative out front. If there's a negative out front, it's going to be below the asymptote. So this one does have a negative out front indicating a reflection, so it's going to be below the asymptote. So all the y values are going to go from negative infinity, and the highest they can go is 5, but they don't ever actually get there. They'll get infinitely close to 5, but never actually get there. Let's go ahead and look at the next example. So here we have a horizontal asymptote at -3, and let's go ahead and get some points down. Now I'll start picking x value 1, so that way I avoid negatives in the exponent. 1 minus 1 is 0. Anything raised to 0 power is 1, and 1 minus 3 is -2. Again, feel free to type these into your calculator if need be to compute it. Now if I pick 2, I'm going to get a negative exponent, and then I'm dealing with decimals and fractions. So instead, I'm going to pick numbers below 1, something like 0. If I plug in 0, I get -1. If I plug in -1, I get 1. If I plug in -2, I get 5. And that's plenty of points. So let's go ahead and sketch our asymptote down here at -3. And then we got our points at 1 and -2, 0 and -1. -1. Ooh, hold on here. Oh, I got that backwards. Sorry. 1, -2 is down here. And -1, 1 is up here. Mismarked a point there. Alright. And then -2, 5. There we go. So there's our function. And if we wanted to figure out the domain here, the domain is always going to be all real numbers, and the range is going to be depending upon the asymptote, and it's either above or below. We know it's above because it's positive out front, so the lowest this thing can go is down to the asymptote at -3. Now we're using a parentheses there because, again, it won't actually ever get there. It'll just get infinitely close. And the highest it will go is positive infinity, is the domain and range there. So let's talk about compound interest. There are many excellent real-world applications of exponential functions, but a very useful one is compound interest because this is, foundational to the world of finance, the idea of compounding interest. So the function for compound interest is given there. Note that balance is a function of time, so t is your variable. P and R and N are all constants, P representing principal, R representing the APR, and N representing the frequency of compounding. So basically every time an account compounds, it basically means all the interest earned over that period is added to the balance. So it's kind of like what's going on with, say, your credit card bills. Most credit cards operate on a monthly frequency, meaning every month they take the interest that was built up over that month and add it to your balance at the beginning of the next month. So in the case of most credit cards, the frequency of compounding is monthly. So let's go ahead and practice with this formula. Suppose we got $800 being invested into an account with a 5% APR compounded quarterly. What will the balance be in 10 years? So A at t is the balance at time t. We don't know that. And here, well, we know the time value. Technically, the time value is 10 years. So let's enter the amount at 10 years. And that's going to equal the principal, which is 800 times 1 plus the rate. The rate is 5%, which is 0.05. N is frequency of compounding, so it says quarterly. Quarterly means 4 times per year. And then that also goes in the exponent slot, and so does the time value. And then we can just type that into our calculator. And I highly recommend, if necessary, type it into your own calculator. If you need to, hit the pause button. Make sure you're familiar with your own calculator. And we're going to round that to the nearest cent, and you should get 1314.90. So that would be the balance in the account after that duration of time. Now, there's a very important constant called E, which is defined there. Now, E is basically the number that happens if you let that frequency of compounding become continuous. So if you look at the compound interest formula, you can see as the frequency increases, the n value increases. If it's quarterly, that's 4 times per year, so n is 4. If it's monthly, then it'd be 12 times a year, n is 12. If it were daily, then it'd be 365, because there's 365 days in the year. So as you can see, if we let the n go to infinity, you're basically talking about a continuous frequency of compounding. And this actually converges to a constant, which is quite fascinating. And that constant is approximately 2.7183. So, in other words, you start getting diminishing returns on the frequency of compounding. And I'm not going to nerd out about this number. I'm going to resist the urge to, but this constant is one of the most important numbers in all of science, actually. It's not just useful for financial applications, but it's useful for a great variety of applications. And that constant E, is often called Euler's constant. And it is the base of the natural exponential function. Alright, let's go ahead and wrap this section up. So we have the formula for continuous compound interest there at the top. Suppose you got $2,500 invested at a 7% APR account, compounding continuously. So when you see that phrase compounding continuously, that just tells you what formula you'll be using. Determine the balance in 12 years. So we know the amount at 12 years is the principal. Now notice it says compounding continuously, so I'm going to use the corresponding formula. So it's going to be E, which is that Euler's constant, 2.78 something, raised to the rate, which is 7%, so 0.07, times T, the time value, which is 12. And we'll go ahead and type that into your calculator. Make sure you take a moment, pull out your calculator, make sure you know where that natural exponential function is in your calculator. And we get approximately 5790.92, rounding to the nearest cent. Alright, cool. Last example. Suppose we got $2,000 put into a savings account with that APR, compounding quarterly. How long will it take to reach $3,000? So here, we want to figure out the time value. We know the amount is $3,000. The principal is $2,000 times 1 plus the APR divided by frequency of compounding 4 times per year because it's quarterly times the 4t. So you can see the tables have turned here. We don't know what the t value is. We don't know the time value, but we do know the balance. So what we got to do is solve this equation. So I can divide both sides by 2,000. That's going to get me 1.5, and let's go ahead and simplify that. 0.04 divided by 4 is 0.01, so that reduces to 1.01 raised to the 4t. Well, crap, how do we solve that? Right, this is not a power equation because the variable is in the exponent's place. And we are at a dead end here. Turns out we need logarithms to solve this type of equation. We need the inverse of the exponential, which is the logarithms. And that's going to be the very next section. So guys, keep up the hard work and just shoot me an email if you have any questions.